Good morning. In the last lecture, I was giving a broad survey of all the different methods in use today in RLADP, and I also commented about the future directions. I started out by focusing on four main questions which define what kind of RLADP method you are using. And what I said was basically a quick summary of a much more detailed survey of the same kind in the book by Lewis and Liu, Chapter 1, where I give many examples, citations of many things many people are doing. When I started talking about these four decisions, the ones I'd like to focus on today are, how do we approximate the value function? This is really the core. We have to decide which value function are we going to try to estimate and use. The J star from the Bellman equation, the lambda, or the Q J prime, which I defined briefly last time, or something else. And the other question is, how do we estimate or train or adapt the weights in the function that approximates this value function? And I didn't put together a separate slide on that, but that's really part of the choice of the value function. Now you can use evolutionary computing, which I mentioned with the Fogel example. You could try to do research on more advanced things, but for the rest of this course I'm going to focus on adaptation as a way to adapt the weights. This is really the brain-like approach, unless you do really sophisticated brain models. So how do we adapt the weights W to approximate J or lambda or Q? And towards the beginning of the last lecture, I showed this slide describing four different types of value function which have been used in existing work. And with these four types of value function, there are actually 5 major methods for adaptation. So today I'm going to start zeroing in on the first and the simplest of these methods so that you can implement it. Not because it's the most powerful, but because the first comes first. And the difficulties in the powerful methods show up in the basic method, which is still very useful in some ways. So I'm going to give 2 lectures really, today and the next one, on heuristic dynamic programming. Later on I'll talk about global DHP, which is another way to estimate the same kind of critic. So today I'm going to focus on this. Today and the next lecture, I'm going to focus on this particular kind of intelligent optimization design or intelligent control design, where there are 3 parts. We have the critic, which approximates the J function. Heuristic dynamic programming, HDP, is the method we use to adapt the critic. But we also need a model if we want to adapt the action network using what I would call the backpropagated adaptive critic. And the idea here is we have derivative signals, we adapt the actual controller, which makes the concrete decisions and actions using this derivative feedback, and we can't get those derivatives. We don't know which way to change our actions unless somehow we train or use, learn a model of the environment we're living in. So the basic idea in this design is to have 3 concurrent systems, each adapted in different ways. Now, in most conference tutorials, I don't have the time to really describe the details of each of these. I'm going to try in the next 2 lectures to get into those details. But in the old days, I would just say, look at the Handbook of Intelligent Control. And there's basically one chapter that tells you how to adapt this one, chapter 10. There's another chapter, 13, that talks about this. And this part is really pretty easy when you've got the other 2. So that's in chapter 3. And they're all up on the web. So far as I know, the only person who's really studied these chapters in real detail is Daniil Prokhorov, who has had some of the most exciting applications of neural network control in the real world in Ford and Toyota. His success proves that it can be very useful to know this mathematics well and use it. So I'm going to talk in more detail about these 3 things. But even after reading the handbook, some people say, This was a little abstract. You gave the general case. Could you be a little more concrete? And could you talk about how it relates to the stuff we understand better, like some of the stuff from adaptive control, also using neural networks at times? So that's what I'm going to do today. I'm going to get deep into a linear example, how these things work out when you happen to pick matrices to be your action network, your model, and your critic. This is a general method that lets you choose matrices or neural networks or anything else. But today I'm going to focus on the example of matrices, which will help you understand the math and give you some exercises. And I'm going to talk about the connection to indirect adaptive control, which is already familiar to many people in control theory. I mentioned before that there are two main seminal textbooks in adaptive control that I know of. There is a textbook by Narendra and Anaswamy and a textbook by Astrom and Wittenmark. Narendra's textbook is perhaps better known in the United States because he teaches in the United States. In fact, Narendra also has a classic paper co-authored with Parasarathi, which really addresses the nonlinear case. His book with Anaswamy really addresses the linear case. But in either case, linear or nonlinear, he has basically developed two methods which are extremely well known in control theory: indirect adaptive control and direct adaptive control. And of course, there were other people who worked on these before he started nailing them down, making them work, proving theorems. In indirect adaptive control, it's basically the same thing. I would like you to go back and look at the past slide in this slide and compare them. In the HDP slide, we are concurrently adapting a model, an action network, and a critic. In indirect adaptive control, we're also adapting a model and a controller or action net, and we're doing so with the exact same mathematics. In some ways, HDP plus BAC is really the same thing as indirect adaptive control, except that we put a critic up here instead of just using square error of trajectory following in the next time period. Now, to make the example simple, to work out the mathematics, today I'm going to start discussing the linear case. In fact, today will be the linear case. In that example, the model network is linear, so the vector x of t plus 1 is equal to some matrix A times the present value of x plus some matrix B times u. This is pretty standard notation. X of t plus 1 is ax plus bu, where x is a vector of length n and m is a vector of length m. And the goal, in general, in indirect adaptive control, is to make the plant follow a reference trajectory, or to go to a reference point where you want it to be. But for the sake of this example, I'm going to simplify things a little by assuming you just want to set this to 0. You want to make your plant go to the origin. 0 error. That doesn't really change the mathematics. It just makes the equations look simpler when I show them to you on a slide. And as an exercise, I would ask you to work it out for the general case, which is not much different. I'm often slipping into the language of control theory when I discuss control theory. When I discuss neural nets or operations research, I'll slip into that language. It's good for us to know all of these languages. But in control theory, people talk about controlling the plant. The plant means that system out there which you're trying to model. Maybe an airplane. If you're trying to control an airplane, the airplane is the plant. So the question is, how do we control it? Well, last time I actually gave the equations for how you adapt these matrices using indirect adaptive control with least mean squares, which is the easiest and most general way to do it. And I showed you all of these equations. I hope you've had a chance to look at them. The thing that's most interesting about it is that every one of these key calculations is very fast. Order of n squared. We have an n by n matrix. It's an n squared calculation just to write all the elements of the matrix. And this thing is so fast, the way you adapt the A matrix is by adding a learning rate times these two numbers. You just do one multiplication, or two multiplications, for each element of the matrix. That's 2n squared multiplications. Same thing with the B matrix. And even for K, to calculate the derivatives of how to adapt the gain matrix, you'll see it's a matrix vector multiplication. And then when you adapt K in proportion to these derivatives with the learning rate, still n squared. So this is a very fast kind of method. But the problem is that it can go unstable. And last time I asked you to think about trying to come up with a simple example. Can you come up with a simple example where this controller will go unstable and fail to control the plant even if the estimate of A and the estimate of B converge? So I'm going to give an example now. I hope you had a chance to come up with one on your own, but now I'm going to just give you one. Okay? And I'm going to show how indirect adaptive control can go unstable even if your estimate of A converges to the right value, even if the estimate of B converges to the right value, and even if the gains, K, converge to what minimizes the control error. Now, if these things don't converge, you're not going to have a good stable controller in any case. But in order to have a good stable controller, it should at least converge to something stable if you meet at least these three criteria. You converge to the right A, you converge the right B, and you converge to the K, which minimizes EC. Now, in giving you that example, the first thing I want to do is show you what K actually converges to if it converges to what minimizes EC. What should it be converging to here? And I want to make the example simple. I suggested you try to come up with an example where n is 2. You have only two variables in the vector x, and u is 1. You only have one degree of freedom in control. M is 1, n is 2. So you've got a 2 by 2 matrix A and a 2 by 1 matrix or vector B. How can it go unstable then? Well, in order to create an example, the easiest thing is create an example where the B vector is just 1, 0. And consider what happens for any matrix A if the B vector is 1, 0. So in that case, our model of the plant is a little simpler. X of t plus 1, these two numbers, are equal to A x of t plus the vector, where the first term is just u, your control decision, and the second one is 0, because you can't generate movement in the 0 direction. And that really follows from this choice of B. If B21 is 0, that means no matter what you pick for u, you're not going to get any action on the x2 variable, but you will get a change in the x1 variable in proportion to u. So this is the simplified model when you make this example of B.